Hello everyone, my name is Zheng. So today I'm going to do a quick code demo with our project 2 linear programming. So here's our entry point. So as you can see that we have two main functions. So one is called part A and then another one is called part B. So corresponding to the part A in the instructions that we form a simple linear programming problems and then solved it with a SciPy. So that's part B right here. So and then for part B, that's where we test with the various m constraints m and then various variable n. And notice that we have LP trails right here. So that's where we run the experiments, run experiments multiple times, and then record average time elapsed and then also average pivots. So here's the functions for run experiment. Very simple, for loop, and then record measure times, and then append that to the list, append pivots to the pivots list, append time to the time list, and append cost to the cost list, and then return averages right here. And then we also have a functions called the random feasible LP. So this guarantees that we always return a feasible LP problem because we generate our X0 randomly, but our BEQ is directly calculated from a matrix multiplications of AAQ and then the X0. So given BEQ and then AEQ, we can it's guaranteed that we will at least have one feasible solution, which is X0. And we also add the bounds for our LP problem because for some of the LP problems, the cost can get as small as we want if it's unbounded. So we just add a bounds here to guarantees that it will always return a best solution. And for our part B, we put everything into a pandas data frame, and then for our plot functions, we read the data from the data frames, and then so right here are just the code to plot different graphs.
Hello, my name is Andrew Hockman. The most interesting result that we saw from our experiments involved the shape of the trend lines we saw as we varied the number of decision variables and constraints. So when we had two sets of graphs, one set where we held the number of constraints constant and varied the number of decision variables, and one where we did the opposite. Now, holding the number of constraints constant and varying n, we see this linear relationship, which is very consistent among all of the m values tested, the only difference being the slope of the line being steeper with higher m's. And this is maybe not too surprising. What is surprising is what we see when we hold the number of decision variables constant and instead vary the number of constraints. What we observe is that for each increase in m, we do initially get an increase in problem difficulty in terms of pivot count and time to solve, but there seems to be a turning point where the problem becomes quote-unquote over-constrained, and we actually see this this turning point where the problem actually becomes easier. It's most prominently displayed on n equals 20. And to test this theory, we actually generated a graph where we went all the way to m equals 50 and verified that even with a n value of 50, we still observe the same behavior where we get this very interesting bell shape. This was not something we expected to see.
And then one of the most challenging aspect of this project is the how to generate a random feasible linear programming function, linear programming problem, because initially what we had is to randomly generate X0, AEQ, and then the BEQs. But it turns out that a lot of those problems don't even have a solution. So that's the reasons why is that we calculate this BEQ based on the AEQ and then X0, and as well as the bonds.